Right. Good afternoon. First of all, just a bit of revision from before a bit of a revision from yesterday. Just close your books, please. Boyle's Law. Let's start off with you, Nikita. Okay, let's hear that, please, Mila. Okay. Right. Right, what is that known as? Good. Right, some of you had to do some writing out for me. Who were they, Luther? Right, can I have your stuff, please? Is that in your science book? No. Your science book's not meant for punishment. You do it 30 times for tomorrow, please. Where's yours? Didn't you have to do it? Did you get it right? Okay, so it was Alberto, Giovanna, yourself, and? Okay, right. I'll catch the other two. Right. Then yesterday we were speaking about temperature and volume. And what we said was, if one heats up a gas, it expands. If one cools a gas, it contracts. So you can therefore obviously plot a graph of volume versus temperature. Okay. Now, up until then, what were the only temperature scales you knew about? Fahrenheit, which we don't use in South Africa. That's an American system. And Celsius, or what's another name for Celsius? Centigrade Celsius is the same thing. Now, what is the freezing point of water in centigrade? 0. Is that the lowest temperature you can get? No. So why, I suppose it makes sense, let's take the temperature of ice as being 0. Anything colder than that will be negative. Anything warmer than that will be positive. But strictly speaking, if you want the real genuine temperature, 0 should be your lowest temperature. Okay, but centigrade doesn't work like that. Can anyone tell me what's the freezing point of water in Fahrenheit? 32 degrees. Boiling point of water in centigrade? 100 in Fahrenheit? 212. Okay. So they got weird, but we don't work with Fahrenheit, so don't worry about that. So that's why when you watch TV and someone says, wow, the temperature is 70 degrees. So what? 70 degrees Fahrenheit. It's not that hot. However, if we plot our graph, volume on the vertical axis versus temperature, 0, 50, 100, 150, 200, 250, etc. And you plot it, you get a graph that looks, forget about this part here, it looks like that. Okay. But if we carry on and we say, hold on, let's plot some further points. Let's cool this gas down to minus 50. We get a point over there. Minus 100, a point over there. Minus 150, a point there. Minus 200, and we see that we get something that looks, so minus 50, there would be the dot, minus 100, let's try and use a Koki pen that's going to work. minus 50, minus 100, minus 150, minus 200, minus 250. Okay? And we can see that this seems to be a solid line, just extending back, straight line. So what scientists then said, let's extend it back to where it cuts the volume axis. Okay? Because obviously where it cuts the volume axis, that means the volume is what? 0. Any further back, we're going to be down onto the negative volumes, which is down this side. Do you agree? That's positive volume. That's negative volume. So if we take it beyond this x-axis, it's now down here onto the negative volumes. All agree? And that's not possible. You can't have a gas occupying less space than no space. Okay? So if that is 0 volume, that must also be the lowest possible temperature. And what did I say yesterday was the lowest possible temperature? Minus 273,15. We normally drop the comma 15 in what unit? No. Minus 273. So there was 100, there was naught, there was minus 100, minus 200, minus 273,15 degrees centigrade. Okay. Then we said, let's override that whole thing. Let's take this axis out. Pretend it never was there. Let's put that axis there. Okay? And let's relabel. Let's relabel this graph. These temperatures here were minus 273,15 degrees centigrade. What the scientists then said is, okay, let's label this as naught. What's the jump between okay, if that's naught, what is the old 0 degree centigrade? 273. What's the old 100 degrees centigrade? 373. Okay, and this was now temperature spelled with a capital T in Kelvin. Notice with Kelvin, what do I not write? I don't put the degrees sign. Okay. Now we can say, what is the shape of that graph? It's a straight line through the origin. But the origin is a genuine origin if we work in Kelvin only. Right, so it only applies if you're working in Kelvin, this directly proportional thing. Straight line through the origin means volume is directly proportional to i.e. volume is directly proportional to what? Temperature in Kelvin. Right? i.e. V directly proportional to capital or lowercase? Capital T. Right. All happy with that? Let's take this a little bit further. Yes. No, there's no maximum temperature. Temperature is defined by the amount of kinetic energy of an object. What is the least kinetic energy an object can have? Stops. Is there any maximum limit to how fast an object can vibrate? No. So there's no maximum limit to temperature, but there is a minimum limit. Okay, so volume is directly proportional to temperature in Kelvin. What do we call this Kelvin scale? It's also known as the absolute temperature scale. So what we're doing now is converting to or from absolute, which is Kelvin temperature. Converting to or from Kelvin temperature. Siyavula doesn't come out too clearly. I think it's not clearly on there. Okay. If we are converting from degrees centigrade to Kelvin. Okay, for example, I say to you, you've got 100 degrees centigrade. Have a look here on the board. You've got 100 degrees centigrade. How much Kelvin is that? What do? You take the Kelvin is equal to the degrees centigrade plus 273. Do you all agree with that? So if I said to you, what was naught in Kelvin? You took the 0 degrees centigrade, you added on 273, and what did you get? 273. What is 100 in degrees centigrade in Kelvin? You took the 100 degrees centigrade, added on 273, you got 373. So you take your degrees centigrade, you add on 273. Right, there's your formula. So let's just do some examples. Right, let's read that number 3. A gas at 250 degrees centigrade and a pressure of 200 kilopascals occupies a certain volume. When its temperature changes to 400 K and its pressure to 150 times 10 to the power of 3 pascals, its volume becomes 800 liters. What was its original volume? Okay, before you do that, I'd like to do numbers 1 and 2. Who is not finished with 1 and 2 yet? Okay, I'll give you 1 minute pulling, and then we're going to mark them. Finished? Right. In number 1, let's pay attention please. In number 1, what are we doing? Are we changing from Kelvin to centigrade or from centigrade to Kelvin? So do we use this formula or do we change it around? That's the formula you use. You take the centigrade temperature plus 273. Here are the centigrade temperatures, so plus 273, and that's going to give us 293 Kelvin. Everyone happy? 293 Kelvin. In B, we add 273. What's that going to give us? 373 Kelvin. In C, we add 273. And what are you going to get? 273 Kelvin. And in D, we add 273. And you're going to get 223 Kelvin. All happy with those? In other words, if you're trying to calculate it in Kelvin, you just add 273. If you want the answer in Kelvin, you add 273. All happy with that? Now, if I give you the temperature in Kelvin and I say, what's it in centigrade? Degrees centigrade are going to be what? Kelvin minus. Okay, degrees centigrade will be Kelvin minus 273. Let's do that. Minus 273, and we're going to get 7 degrees centigrade. Minus 273 from that, and what are you going to get? Minus 223 degrees centigrade. Don't forget the degrees now, okay? When you're working in degrees centigrade, it must be degrees. Minus 273 is going to give us 100 degrees centigrade. Minus 273 is going to give us 0 degrees centigrade. All happy with those? Nice and easy. Make sure you know how to do them. Now you can do number 3. While you're doing number 3, I'm going to write up number 4 on the board, please. Number 4 will be for homework. Number 3 you do in class. Right, people, have you all finished this one over here? Let's have a look at marking this very quickly. What formula are you going to use? PV equals nRT or P1V1 over T1 equals P2V2 over T2? Okay, I haven't given you in this sum, have I spoken about the number of moles or the number of grams or anything like that? So no. So it's purely, so this is number 3, eh? P1 V1 over T1 equals P2 V2 over T2. Right, we need to know what P1 is, what V1 is, what T1 is, what P2 is, V2, and T2. A gas at 250 degrees centigrade. So that original temperature is 250 degrees centigrade, agreed? And a pressure of 200 kilopascals. Occupies a certain volume. We don't know what it is. When its temperature changes to 400 Kelvin and its pressure to 150 times 10 to the power of 3, what, pascals? Its volume became 800 liters. What was its original volume? Okay, so is that pressure okay? Is that pressure okay? They can't be in different units, they must be in the same unit. So I've either got to divide that by 1,000 or times that by 1,000. Which one do you want to do? Can I just take this off and make it kPa? Divide by, so take out that 10 to the power of 3. Okay, so that becomes 150 kPa. Can I work in kPa? Right. So that becomes 150 kPa. I divided it by 1,000 to bring it to kilopascals. That means the 10 to the power of 3. This bit disappeared. Okay, temperature, 250 degrees centigrade, 400 K. Can I change this one to centigrade? Change that one to Kelvin? Yes, they must always be in Kelvin. So what does that become? 273 plus 250 is going to give me 523 Kelvin. Volume at 800 liters, is that okay? But what will this volume be in? Liters, okay. And now I can just substitute 200 V1 over 523 equals 150 800 over 400. And can anyone tell me what V1 works out to be? 784,50 liters. You're working to 2 decimal places, please. So if it's no extra number, you put a 0, okay? Then you would have got 0,78. Okay, that's fine. That will be fine. Right, all happy? Homework? Please do that one, number 4, up there for tomorrow, please. Thank you very much.